So now let's review this whole system. This is the one neuron, a single layer, one neuron perceptron. And here we have the input X, the weight W, and the output D. So here the input is for this problem is the coordinate. It's the x1 and x2. If for any pixel, if we know x1 and x2, we can know their location. We also call the input as the regressor. So that is the input. And then it's the weight vector. So here's W. And W in this problem is equal to W1 and W2. That's their weight. Of course, we have another extra input, is the B, is the bias. For the bias, we here fix the bias equal to 1. Therefore, we only need to adjust its weight, is W0. So we call the weight as the stochastic environment. This one could be changed. We have an initial weight, and then we want to find the optimal weight. We have input, we have weight, and then we will have an output. So very easy to find out the output. The output equal to nothing, but the input multiplied with weight and then sum together. The summation then goes through a activation function, and the output will be the actual output. Here we have a desired response, or called a desired response. That one is just any point is a feature. So here, for the red group, they all equal to 1. The 1 is their desired response. For the blue one, the output equal to -1. So the -1 is all this blue point desired response. So here we have all this input, weight, and the desired output. So here for this computer experiment, the goal is to find out the optimum weight. So we can give an initial weight based on any guess, or based on you can use MATLAB, can give you a random weight. The random weight doesn't really work because it have any possible value. Here we want to find the optimal weight. So here the goal is how could we find the optimal weight? So we follow this flow chart. We have all different input that's corresponding to the red point and the blue point from previous slides. Of course, adding a desired bias of 1. So this one all goes through the neuron and the activation function. We have output, the actual output. This one not always the yi, the actual output, not necessarily equal to the desired response. It could be equal to each other until the system is perfect. You get the optimum W0, W1, and Wm if you have M input. If these two, the actual output and desired response, equal to each other, that weight called the optimal weight. So the goal is how can we find the optimal weight? So this is how do we do. We know the output, the actual output, and then we compare the actual output with the desired response. So they are different, correct? Therefore, we will have some signal called the error. We are going to change or adjust the weight, use the error information, and then we can adjust all the weight. So this is what we need to do for this computer experiment. So before we can discuss how can we update the desired response, how can we update the weight, there's one terminology we need to learn. That one called the cost function. Here we're using the epsilon w to indicate this is the cost function. Then question is, what really is the cost function? So if we forget all this terminology from our textbook or from any internet, just using our own language to describe this cost function. This is my definition. The cost function is measures between the actual output and the desired response. So this is basically my understanding of the cost function. About the definition of a cost function, there could be different definitions. One could be called the instantaneous error energy. So just for any single input, you will get an actual output. And then this one different from your desired response. We call that one square is the instantaneous error energy cost function. Or another way is if you have n different input data, and then you can calculate the error, the bias for all of them, and then you find the summation of the instantaneous error energy. We call that one as total instantaneous error energy. So this is two ways to define the cost function. Since the cost function is the variable to describe the difference between the actual output and the desired response, therefore, we want to make the difference as smaller as possible, and we call that one is the optimal synaptic weight. So, for example, we assume just arbitrarily give a curve. This is a cost function curve. The W is when you do the adjust all this synaptic weight, what's the output of their cost function? So at the very beginning, we give any random or arbitrary weight to the synaptic weight, as the synaptic weight, and we will get their cost function. So this is the output of a cost function, the epsilon W 0. 0 means the initial gas or the input or the initial weight. So then what we do is we adjust the weight. Which direction we want to adjust the weight? The direction is we want to make the optimal weight, we want to make the cost function smaller. That is the direction we want to adjust the synaptic weight. So then, for example, after we adjust the synaptic weight, the cost function going to move to here. Okay, this one's good because this is getting smaller number, but it is not enough because we want the cost function as smaller as possible. Therefore, we keep adjust the weight, makes the cost function become smaller until it reaches the minimum value. And we call that one is the optimum synaptic weight. And then at this point, the cost function reaches its minimum value. So look at the cost function, and we want to make the cost function reach the minimum value. And based on there, we can find if we can find the derivative equal to 0. That's equal to the minimum cost function. So now back to here, we know what is the cost function, and our goal is to make the cost function like what we show here, make the cost function reaches its minimum value, and then we can get the optimal synaptic weight. So in next video, we will show how can we get the optimal weight, which can make the cost function reaches its minimum value.